have been looking at the Schrodinger equation for spherically symmetric systems, and we have shown that H and L square is equal to 0, which implies that L square is a good quantum number, and the Hamiltonian we have shown is minus h cross square over 2 m d by dr r square d by dr plus L square operator over 2 m r square plus V r, and therefore, the Schrodinger equation is minus h cross square over 2 m d by dr r square d by dr times psi plus L square operating on psi 2 m r square plus V r psi equals E psi. I could tell you that psi r vector can be written as r, which depends only on r, and some other function which I have given as y, l, m, theta and phi, and then write this and do separation of variables, and what you would find is that the equation becomes minus h cross square over 2 m, there is r square here, 1 over r square d by dr r square d r by dr plus L plus 1 h cross square over 2 m r square r plus V r r equals E r, and that is because y l m's give you this L plus 1 term. Let me do this explicitly and show it to you. So, when I have minus h cross square over 2 m 1 over r square d by dr of r square d psi over dr plus L square over 2 m r square psi plus V r psi equals E psi, and write psi equals some function r of r, other function which I am writing y, theta and phi, then what I get is minus h cross square over 2 m 1 over r square, the full derivative of r square d r by dr times y plus L acts only on those functions which are functions of theta and phi, because it involves no derivative with respect to r. So, I get r over 2 m r square L square on y plus V r r y equals E r y, and then you divide this whole thing by 1 over r y and multiply by r square to get minus h cross square over 2 m 1 over r d over dr r square dr over dr plus 1 over 2 m y L square y plus V r equals E. And then I change sides of certain terms and write this as minus h cross square over 2 m 1 over r d by dr of r square dr over dr plus V r minus E is equal to minus 1 over 2 m y L square y. And it so happens that this term, the term on the left hand side, depends only on R. Term on the right hand side here depends only on theta and phi, and for them to be equal, therefore, this must be equal to some constant lambda. And therefore, what you find is that minus 1 over 2 m L square y is equal to lambda y. Immediately you know that this is the eigenfunction, y is the eigenfunction for L square, and therefore, lambda should be equal to nothing but minus L plus 1 h cross square over 2 m in this case, because there is an extra 2 m sitting here. And you bring it back to the R equation, and the equation you end up getting is minus h cross square over 2 m d by dr of r square dr by dr, and there will be a 1 over r square in front, plus L plus 1 h cross square over 2 m r square r plus V r, r equals E r. So, the energy E depends on L and radial function r only. So, energy E depends on the angular momentum as is expected, higher the angular momentum, more the kinetic energy, and E depends on R through potential V r. So, you notice that the angular part of the wave function for spherically symmetric potentials is the same. So, angular part of psi for spherically symmetric systems is the same for all V r. And what is it? These are eigenfunctions of L square operator. It is only the r component that differs, and that depends on V r. So, my psi is nothing but r, y, and I can write this y, L, m, theta and phi. So, psi is also, now psi is an eigenfunction of L square and Lz as is expected, because these are conserved quantities, and in addition I get this r, and the equation for r is minus h cross square over 2 m 1 over r square d by dr r square dr by dr plus L plus 1 over 2 m r square r plus V r equals E r, and this can be written further as minus h cross square over 2 m d2 r over dr square minus h cross square over m r dr over dr plus L plus 1 over 2 m r square r plus V r equals E r when you expand this. Now, this equation involves both the second derivative and first derivative r. We would like to simplify it, but before that let us say that r should be finite everywhere, because psi should be finite. If whatever solution I find, r should be finite everywhere, including r equals 0 and r going far away. For bound states, r should go to 0 as r goes to infinity, because for bound states the particle cannot escape to infinity. So, now what we are going to do is simplify this equation by writing r in a certain term. Or before that, I should also mention that dr over dr should also be finite everywhere, and this finite, and with this also there is one more condition, they should be continuous. So, finite and continuous should also be finite and continuous everywhere. Let us now simplify this equation. So, the equation I have is minus h cross square over 2m d2r over dr square minus h cross square over m r dr over dr plus L plus 1 h cross square over 2 mr square r plus v r equals E r. Let us write r equals u over r. And since r is finite everywhere, u should go to 0 as r tends to 0 faster than, and maybe equal to also. So, u should go to 0 as r tends to 0 faster than r, or as r. Okay, then only r would remain finite as r goes to 0. But what it does, so in addition to this condition that I have on u, which I am going to apply, what this substitution does is simplifies things for me, because now dr over dr is going to be du over dr 1 over r plus or minus 1 over r square u, and d2 r over dr square is going to be equal to 1 over r d2 u over dr square minus 2 over r square du over dr plus 2 over r cubed u. Let us now substitute this in the Schrodinger equation here and get minus h cross square over 2m, substitute for this 1 over r d2u over dr square minus 2 over r square du over dr plus 2 over r cubed u minus h cross square over mr, in the bracket I get 1 over r du over dr minus 1 over r square u, then I get plus L plus 1 over 2 mr cubed u plus Vr u plus is equal to E u over r, V u over r here. Now, let us cancel certain terms. The term with du by dr cancels with du by dr here. The term with u over r cubed cancels with this term here. So, all I am left with is minus h cross square over 2 m u double prime over r plus L plus 1 h cross square u over 2 mr cubed plus Vr u over r equals E u over r, where u double prime is nothing but d2 u over dr square. Multiply by r throughout and the equation becomes minus h cross square over 2m u double prime plus L plus 1 h cross square over 2 mr square plus Vr u equals E u. This is like the Schrodinger equation for one dimensional motion, except that this Vr also has an additional term here, or there is a u here. Recall from classical mechanics that in motion in central forces, there was a V effective which was VR plus L square over 2 mr square. So, this term here is very similar to that. You get a V effective which is L square over 2 mr square, except in quantum mechanics I get L plus 1. So, the equation is nothing but minus h cross square over 2 m u double prime plus V effective R u equals EU, exactly like 1D equation where V effective R is VR plus L plus 1 h cross square over 2 mr square. Now, for potentials that are regular near r equals 0, some general properties about r can be inferred from this equation. So, the equation that I have is minus h cross square over 2 m u double prime plus L plus 1 h cross square over 2 mr square plus VR u equals EU. So, VR that goes as maybe minus 1 over r, or better I mean it does not blow up faster than 1 over r. The equation becomes minus h cross square over 2 m u double prime plus L plus 1 over 2 mr square u is equal to 0 as r tends to 0, because I can neglect EU, I can neglect VR, and therefore, this is the equation that becomes. And if you solve this, you basically, if you rearrange terms, you get u double prime minus L plus 1 u over r square is equal to 0. If I take u to be of the order of r raised to alpha, you get alpha minus 1 minus L plus 1 is equal to 0. So, alpha could be either equal to minus L, or alpha could be equal to L plus 1. So, your solution u r as r tends to 0 goes as either r raised to minus L or r raised to L plus 1. So, what we found is that u r goes as either r raised to minus L or r raised to L plus 1. We want u r over r to be finite as r tends to 0, because r should remain finite, and therefore, r raised to minus L solution is not acceptable. So, u r as r tends to 0 goes as r raised to L plus 1. The solution of the Schrodinger equation as r tends to 0 goes as r raised to L. So, you see that r depends on L. Now, through this we find out. So, that is one property we can see for u from here. Now, other properties as you go far away, r tending to infinity and all that, those will depend on what VR is like. But this is a general thing that you can find out from the u equation. And what we will be solving now is the u equation, because that is easier to solve. So, let me just now conclude this lecture by saying that we have written the Schrodinger equation for a general spherically symmetric potential VR, and then by writing the radial component where psi is given as the radial component times y, lm, theta and phi, we have found that The equation for R is 2m 1 over r square d by dr, r square dr by dr plus L plus 1 h cross square over 2 mr square r plus Vr equals Er. Then by writing R as Ur over R, we have found the equation for U, which is like the one-dimensional equation U double prime plus L plus 1 over 2 Mr square U plus Vr U equals Eu, which is equivalent to minus h cross square over 2m U double prime plus V effective R U equals Eu, and we finally found for irrespective of Vr, as long as regular, doesn't blow up faster than 1 over r as r goes to 0, r goes as r raised to L as r tends to 0. In the next lecture, we are going to focus on a particular system, and that will be the hydrogen atom.